Okay, I think we can start then. Hello and welcome to our session about Kubernetes, taking Docker to the next level. First of all, we want to introduce ourselves. I am Marc Sluiter, as we say in Germany, because that's where I come from. I'm working for a little bit more than half a year now for Luminis Technologies, and I'm a Java developer for almost 14 years. My main project is the Untitled project, which you just heard about. Then I'm also busy with our Amdatu project, and in my spare time I'm playing around with a little bit Android and the Internet of Things. For example, with a Raspberry Pi controlling some LEDs, Lego Mindstorms, or Leap Motion devices. On Twitter you can find me under the Twitter handle @Slinters.
My name is Willem Janssen. I'm a software architect at Luminis Technologies. I also work on the Untitled project. I'm going to explain a little bit more about it later on. And I'm also, as you can see from my shirt, participating in the Amdatu projects. And I'm a PMC member for both Apache Ace and Apache Felix. If you want to Twitter me, then you can use that hash. So, our previous speakers already mentioned what Untitled tries to achieve, but he didn't mention yet what actually it is. Untitled is an open innovation project, which includes a couple of companies, including Thales and ourselves, Luminis. And what it tries to do is it tries to create a reference architecture that creates an implementation for intelligent, robust, time-critical systems that are also running in the cloud. Which is also why we're giving this talk, because Kubernetes is something that's being actively going on in the cloud. And first, Mark will explain a bit about the backgrounds.
Yeah, as you heard already, we want to deploy several services in the cloud, so we have some requirements when doing this. We want to run several services on one node in a cluster, but these services should be isolated from each other. And what we want is portability. This means that you don't have to care about which service is running on which node with the technical details. You just don't want to care about that. There is already a solution for this, virtualization. We have two kinds of virtualization. First of all, you have virtual machines. And second, we have lightweight Linux containers. The difference is that virtual machines run a guest OS on each virtual machine. And with Linux containers, you have only one host operating system, which is shared between the containers. Linux containers are not a new technology. They are around for already 10 years. It's based on Linux kernel features like CNAMEs and namespaces. There are already some tools around for a longer time which make using Linux containers they want to make it easy. For example, LXC, libvirt, or systemd einspawn. But these tools are quite technically, and they have not a nice user interface, and they are quite hard to use. Then in 2013, the Docker came to market, which made using Linux containers much more easy. The main features of Docker are portability. Your service, which is running in a Docker container, always has the same environment. You don't have to care about on which cluster node it runs. Then the API and the tools of Docker are application focused. So you really care about your application which you want to run in the container. You don't have to care about the technical details of a container. Then there are so-called Docker files. These files are plain text files in which you define what should be installed in a container and which should be started in a container. These Docker files can easily be shared, or the images which you build out of these Docker files can also be shared in a Docker registry. There's a big public registry hosted by Docker itself, and you can also host your private Docker registry for your images. And last but not least, because of its open API, there's a really evolving ecosystem around Docker. Nearly each day there is a new tool which is dealing somehow with Docker. Okay, now we know we want to use Docker containers for our use case, but there is a problem. How do we orchestrate these Docker containers in a cloud? On your development machine, only locally, it's no problem to start and stop these containers manually, but you really don't want to SSH into each cluster node for starting and stopping your containers. So we searched for a tool which can handle this, and Jan Willem will talk about one tool which we found.
So the tool is Kubernetes. Kubernetes is originally started by Google for their Google Cloud Engine, and they started it using the best practice they already did and had for their own data center. So Kubernetes tries to leverage containerization. It tries to solve the orchestration problem Docker has, plain Docker has, and it tries to provide you also with a framework and API to extend on that. For example, if you do not like the way your Docker images are scheduled, then you can simply swap out the existing scheduler system for Kubernetes and use your own. As I said, it is developed by Google, but it's no longer a private to Google. Google open sourced it a couple of years back. And since then, it's actively being picked up by large companies, including IBM and Microsoft, Red Hat. Well, it's unfortunate that my speakers are gone, slides are gone, but let's go on and discuss a couple of concepts that are present and used in Kubernetes. First of all, it obviously leverages Docker images. But for that, it needs a couple of assumptions for the Docker images. Docker images should be small and lightweight. The reason for that is that it should be scalable, horizontally or vertically. So this means that if you want to have a couple of Docker images that are shared or use shared storage facilities, then you need to somehow make sure that those Docker images can access that shared storage facility. So this means that you somehow need to describe which Docker images form a logical, cohesive unit. And this is what in Kubernetes is called a pod. So a pod describes what Docker images are running closely next to each other on a single node, or as Kubernetes calls it, a minion. And each pod can be scheduled for one or more nodes. Ah, my slides are back. So pods are scalable. They can be run on many minions if you want. They can be created replicas for each pod, which means that you have a kind of failover scenario that you can support. And they form a logical unit. Why do you want, for example, to support multiple containers in a single pod? Well, that depends perhaps a bit on your application, but consider a web service that has a local application cache. You simply want to have two small Docker images, one for the cache, one for the web service. And you can upgrade and deploy both of them independently of each other, but they still cooperate as one. On to the next concept. So we have now something that describes what we can run. And the other concept that belongs closely to that is a replication controller. A replication controller simply has one purpose, and that's to manage the lifecycle of pods. As I mentioned, the pod describes what Docker images you want to run, but it also describes what the desired state of your Docker images is. For example, I want to have a web server deployed, and I want to have, for failover scenarios, at all times, 3 instances of that web server running. This is done through the replication controller. The replication controller ensures that at all times 3 pods are running. If there are 4, it simply kills one. Why? To enable to reuse those resources for other pods. If there are 2 pods running, it fires up a new pod to ensure that the minimum requirement of 3 is retained. An interesting feature that can be done using replication controllers is to have rolling updates. This can be done by scaling down your old version of your pods to a single instance and gradually upgrading the number of pods of your new version. So there's an interesting concept that can be used through replication controllers. So we have described what we're going to run. We have described how it should run, how many instances it should run. But it still runs in your data center. It's not exposed yet to the outside world. And we want probably to have users access your service from the outside world. So we need somehow to explain which port should map to what service, or what port of your Docker image should be mapped to the outside world. And this concept is called a service in Kubernetes. So a service does nothing more than describe how to access ports of your Docker images. So more or less, service acts as a proxy for your service. And a service can also be used to load balance your traffic between the various pods. If you have 3 pods running, then it will automatically, by default, round-robin scale route every traffic to each of those pods. So in a sense, you can also think of a service as being a bridge between the internal network, your private, safe environment, and the external world. So we have now discussed what we can run, how we should run it, how we can access it, but we have not talked about how to control it. This is the control plane. So typically a control plane in Kubernetes is called a master node. And a master node is a thing that runs on a more or less dedicated machine, and you can invoke APIs on it to, for example, scale up or scale down your pods. The control plane also, the master node also retains the state. So if one minion goes down for whatever reason, it knows that that minion was there, and it can ensure that somehow a new minion is started and all state that as it was before the node went down is restored. Another aspect of the master node is that it also schedules your pods. As I mentioned, the pods are probably also used for retaining and making sure that the number of services you want to have running are kept running. So if you have 3 pods, then it can also schedule the amount of pods that you want running. Later on, Marc will discuss and show a demo that we've picked from the Inetics project. So first, before we go into the demo itself, I'm going to first explain a little bit what the actual application we're going to demo is about. As I said, it is the Inetics demonstrator. It's a part of a demonstrator we've made for the Inetics project itself. And it's a simple producer-consumer application. And for this simple use case, we've implemented something that processes sensor data. So how does it look like? At the left side, you have various sensors. Don't care really what those sensors are, but let's assume that they provide you data. The data is stored into a queue. And for each sensor that produces some raw information, you want to process that. And once processed, you want to store it somewhere in a data store for later use. For example, to show it in a nice graph, or process it further, or make management boards of it. As you probably can see, if we simply assume that each of those services or images is its own dedicated Docker image, you can see that there are probably scalability issues going to arise. If you have many sensors that put data onto a queue, if the process can't cope up with the amount of data that's been put up on the queue, then you have potentially a problem. So you want to have scalability at various levels, at the processing level, at the processor level, maybe also in the queue and data store level, but that's not in this demonstrator yet. So if we go into a more technical detail on how the deployment of the application itself is done, for this we have a virtual machine. Actually, we have 5 virtual machines. One is the actual controller. On this, the master node is considered. It's the control plane. On this, we have the replication controllers for each of the parts. It also, because we needed to host it somewhere, provides the viewer service, the web front end we have developed. And it also hosts some auxiliary state information in the form of a Docker registry and an SD database. As I mentioned, the replication controllers ensure that the number of pods that we have described are actually running. And this means that, for example, for this producer, we've mentioned that we have 2 replicas running on node 1 and on node 2. 2 separate instances are running. Same goes for the queue, for the data store and the viewer. So all the actual parts of the application are being processed and run on the various nodes. What node exactly runs what part of the application, I don't know, I don't care. I should not care, because Kubernetes will ensure that if I want to access something, that I can access it by means of the service declarations we've made. So, onto the actual demo. Mark.
Okay.
Here.
So, first of all, I want to show you how you create such a replication controller and services and pods. So, let's start with a replication controller. Can you see this? Should be big enough. In Kubernetes, you can define everything in JSON or in YAML files. We choose the JSON. Here it starts with a replication controller. This replication, for each component, you can assign some labels. In this case, we have one label called name with the value analytics processor controller. And this replication controller has a so-called desired state. This desired state is always compared by Kubernetes with the actual state of the running components. And if something is not the same, it will try to make it the same. So our desired state is that we want to select the analytics processor pod, and we want to run this twice. We want to run 2 replicas of this processor pod. So one thing is a little bit weird at the moment in the Kubernetes version we use. The pod definition is inline inside of the controller definition. So here starts the pod definition. Again, you can assign labels to it. It also has a desired state. And the desired state is we want to have one Docker container in it. So, and this Docker container should be based on this image. You want to run this command. You can set some environment variables, and you can define some port mapping. So basically, this is what you provide with the Docker run command if you do it manually. Then the next thing is a service. It's also a JSON file of a kind service this time. The most important part here is we want to intercept traffic to this IP address. This is the IP address of our virtual machine which we run, which hosts our Kubernetes master. And we want to intercept the traffic on this port. And we want that this traffic is routed to the data store viewer port. And the container port on which this pod is listening is port 8080. So basically, all traffic to this IP address on port 80 is forwarded to the pod. I don't care where it is running, on which node, on port 8080. So now we have these files. What I already prepared. I have six virtual machines running, which is simulating our cluster. The booted Docker VM is not important here. We have one controller VM, which is running the Kubernetes master, our private Docker registry, and the etcd key value store for configuration data, which is also used by Kubernetes itself. And we are running 5 cluster nodes, which are running the Kubernetes minions. So here I'm logged into the master node via SSH. First of all, I can show you the kube control command line interface of Kubernetes. I want to see our minions. Here you can see we have 5 minions ready. Can you read this, by the way? Or should I make it even bigger? Ugh. Why does this always happen? I can also check my replication controllers, nothing there. I can check my pods, nothing there. And I can check my services. There are only 2 internal Kubernetes services available at this moment. So now we want to start our own services. Nope. This is done by a simple command to also the kube control command with the create -f and then it pointer to the file where our service definition is in. So we can just run it. Create services. And the same for our replication controllers. Here we start 5 controllers. So everything should be started now. Now we can again check our replication controllers. Now we see 5 controllers are running. 4 of them only running with 1 replica, which means the corresponding pod will be started only once, and our processor pod is started twice. So let's have a look at the pods. Unfortunately, in this resolution, it's spread to 2 lines for each pod. Can make it big. So here you see that at the moment the status of each pod is pending. What is happening now? The application controller is choosing a minion, is starting the Docker container on this minion, which will download the image from our Docker registry, start the container, then it will install some OSGI bundles, basically the same or something similar to the thing which you saw in the presentation before us. Can also check our services. You see we have now 2 own services. The second one is the important one for us, the viewer service. Let's see what our pods are doing. Pending. Okay, so we have to wait a minute.
So let's hope that the demo gods are with us.
Yes, that is what I hope now too. This doesn't look too good.
Oh, well, we can describe it perhaps.
It's even not downloading anything. That's not good.
Is it because of internet connection, perhaps?
It should have everything locally. Not only should, it has.
Okay.
Yeah, too bad. Now the demo is not working, which is not nice. But the time is running away anyway. So what should have happened is that the pods were deployed on the minions, where the service will will provide an interface to our website, and we don't have to care on which minion this website is deployed. Then the idea was that we have too many produced data and too less processed data, so then you can resize your replication controllers on the fly with this won't work now. Oh, okay, it says resized. So you can say kube control resize replication controller and index processor, and with a new number of pods, you can do this with the command line tool, or there is a REST-like interface to the API server of Kubernetes too, so you can integrate Kubernetes into your own environment. Too bad that it didn't work. No, one last try. No. Pending. No. Sorry, I have no clue why this does not work yet. So, at this point, are there any questions? No? Then we can provide some links to the related technologies.
Yeah, this demonstration itself is also downloadable from the GitHub repository. You might have a decent laptop, lots of memory. 16 gig is at least necessary. If you want to know more about Kubernetes itself, kubernetes.io. If you want to know more about Enetics, there's a website for that, Amdato, Dito, and we are from Luminis. If you want to know more about our company, well, probably you already know, but luminis.eu is our website. And that was the last part.
Okay, thank you.